out. We went on to do that and actually found that the same system, which essentially operates like a thermostat to measure oxygen levels and change many aspects of the cell's function and of systemic physiology, was actually widespread. It was in all cells in the human body, indeed in all animal cells, and has many other functions other than the regulation of erythropoietin. So sometimes that's one thing that we will find in science, that the importance of a problem only becomes evident after it has been solved. And that was our happy experience, that we chose a problem for its tractability. And then we found later on that the solution was more important than our wildest dreams at the start. So that was a very fortunate position for me. I can go in, I can hear your questions. I can go in a little bit more to the selection of the questions, the experiences that brought me from a practicing physician into science, and some of the difficulties and positive aspects of managing a dual career. But perhaps I pause there and see if anyone has any specific questions, and then if they don't, I can carry on, or Yelizaveta can prompt me to say something you might find interesting. I'll just pause for a moment. Nothing for the moment.
So our students are a little shy, so I pose a little question to you. If there was like a moment when you want to give up all this, give up your research and start different action, and how did you handle it? How did you handle this demotivation?
Yeah, I don't think there was ever a time when I wanted to give it up. There were times when things went badly, for sure. And in discovery science, unfortunately, most things will go badly. That's because of the complexity of biology. I can go into why biology should be so complex and so perverse, so difficult to understand. But many or most of your predictions are not borne out. I'll give you one example, perhaps, which is interesting. It was an up and a down. We as I've said, the system that we work on was much more important than we thought. So we thought that we were going to understand the regulation of erythropoietin by the kidney. And as I said, I decided to do that because I thought there might be an answer to that question, a discrete answer. Some people said, well, that's not very important. If you want to be an important person in science, you should work on the regulation of blood pressure or the cause of nephritis, inflammation of the kidney, like everyone else. But I didn't do that. I didn't believe them that those problems were going to be tractable, answerable in my hands. Too many other people looking at them. So I chose this EPO regulation problem, which some people said, that's a little thing. It's not that important. We have erythropoietin. We don't need to understand how it's regulated, do we? Or at least we don't need to understand it very much. But we did an experiment. We found at every, some of you I think will know this, that at every gene there are control sequences, like an address sequence, and they confer the regulation by oxygen. They encode it. And what we did is we found those sequences from the EPO gene, and we put them into cells that don't make EPO. We linked them to other genes, and they still worked in the other cell. So that doesn't make EPO. And the implication of that was that the system was in all cells. It wasn't just making EPO, but it was operating with the sensitivity of EPO. So I was very, very excited about that. And once we consolidated the findings, we wanted to publish the work, which is important for you as a scientist. We wanted to publish it in Nature. I was so keen that I actually drove to the Nature offices in London with the hope of meeting an editor who I would persuade should publish the work immediately. They didn't do that, and it took 4 months for the paper eventually to get rejected, which was an enormous disappointment to me. I was massively frustrated, almost, well, I was angry about it. One of the things they said is, though they delayed and delayed and delayed, they said we couldn't find referees. My argument was the results were so clear you hardly needed referees. Though the reason they couldn't find the referees was they were interested in finding experts in the field. There was no field. It was a new field of investigation, and they apparently couldn't find expertise. So that was bitterly disappointing to get that rejection 4 months after driving to the offices. Of course, everyone's got their dream. We were a little bit arrogant. We kept the letter because we knew the findings were important, and we foresaw the opportunity to have a little joke about that letter. So I now have 2 letters on the wall behind me. One is from the Nature magazine in 1992, rejecting the paper. And the other is from the Secretary of the Nobel Assembly in 2019 with news of the award of the prize. So that's a little story about, I guess you just carry on, never give up. You know who said those words, never give up? Winston Churchill, and they're obviously relevant to the current situation.
Thank you, thank you. We have a question from our student. Why are you interested in hypoxia?
Why am I now interested? I've given you an answer as to why I got interested in it, but people get very good at explaining themselves. So I don't always admit that I just started on EPO more or less at random because I thought it was a soluble problem. If I want, I can persuade you that what I was very clever, and I saw the extraordinary importance of oxygen. Oxygen is important to human life. The lack of oxygen will put you in trouble in seconds and kill you in a couple of minutes. It is important in most, if not all, human diseases involve the dysregulation of oxygen supply to one or other organ. So in heart attacks, it's lack of oxygen to the heart. In stroke, it's lack of oxygen to the brain. In cancer, there's a problem that the cancer must get oxygen to grow. So the balance of oxygen supply and demand is important to cancer. So now the possibility of therapeutic manipulation of this system is important in medicine, perhaps, although who knows, it's very difficult to predict the outcome of medical intervention in biology. And that's something that drug companies are working on at the moment. There are drugs that manipulate this system. But it'd be wrong to say I saw the massive importance of oxygen, and therefore I picked an important problem. I picked a tractable problem. actually was an unfashionable problem at the time that we started, and that's fundamentally important to you. It's possible that you will argue as scientists that the Ukraine does not have the resource to do this, and that's probably true at the moment. And it may be true for many years to come that the resource is greater elsewhere. And I'm going to tell you that I don't think this matters too much. What a lot of resource will do is bring in a lot of people to that field, which will then be highly competitive. And that fashion will seduce you. You will enter that field because you find those people or their work inspiring. But don't. The field will be either crowded or intractable or both. So the bottom line is you must be brave. You must have your own field, your own question, or one that's not prominent in other people's minds, and take the risk that you can solve it. That's very, very, very important. And all the world will drag you otherwise. The whole of peer review, people, as I said, that people wouldn't publish our first work. That's because the journals like to publish in popular subjects where they can, get their citations. The funders are all controlled by people who think they know the important problems. So it's more difficult to get your funding. But you have to do something different. Think about it. If there are 10,000 people working in a field, how is it that you, as an individual, are going to make much of a difference? You might, but you probably won't. If you do something unfashionable out on your own, you might just succeed and do something that no one else has been able to do. And that's a very satisfying thing. But a good question. Thank you.
Thank you. So next question is, did you know about the connection with cancer before your research for Nobel?
It's a good question. The answer is no, we didn't really, or at least we hardly knew about it for the reason stated, that I was interested in EPO regulation, because if you donate a unit of blood, your kidneys will make EPO at precisely the right amount to replenish that unit of blood, and you don't get too much blood, you don't stay with too little. It was that position that we sought to understand, and didn't foresee the general importance to cancer, though it was true that we well knew that kidney cancer, which of course can affect the EPO producing cells, does sometimes produce too much EPO. And in the end, that was a clue. That was the clue that one of my co-laureates, Bill Kalin, deployed in coming into the field and understanding that there was something about kidney cancer that dysregulated this system. But the broad answer to that good question is no, we didn't foresee it.
Thank you. So next question is how to understand whether a person is suitable for the research activity. Is scientific job different from some job in other industry?
Just say that again. Your voice cut up a little, and I missed you there. So, Sveta, could you say that one again for me? I'll just turn you up in volume. Yeah. Can you repeat the question for me, please?
Yes, of course. How to understand that the person is suitable for the research activity? Is scientific job different from some job in other industry?
Yeah, no, that's a good question. Well, I don't think you'll ever understand whether you're suitable for something until you do it. There are so many complexities. decision making in life, you will have your decisions to make. Just make them, you know. Your trajectory through life, it will be affected by the decisions you make. But more important than the decisions you make is what you do with the consequences. There's so many external things that will affect your life that your own decisions are only a very small part of that. And people, particularly as you get a little bit older, tend to worry about those decisions. It is, I mean, what you will need to be as a discovery scientist, that there is a counterpoise in that you need to be someone who is very driven, but you need to be also someone who is very open to finding out that they're wrong and doing something about it, reformulating a hypothesis. So that is some people find that difficult. Highly driven people, you know, if you were top of the class, you probably know that if you work very hard, you become top of the class. Yeah, some people are like that. The problem that you will face is in research, then if you're asking a genuine question, a genuine hypothesis, that hypothesis may be true or false. And doesn't matter how hard you work, if it's false, it's false. So you have to be that sort of person that can cope with that. I should be clear, you don't have to be very clever. It might even be a hindrance. The biology is very perverse. We're made by Darwinian evolution. The way our bodies work is not always very logical. And people who think over issues, who form hypotheses that are too complex, they may have trouble. I didn't pay much attention to the decisions I made. This may surprise you. I remember deciding to do medicine, and the conversation went like this. My name's Peter Ratcliffe, and in formal education in the UK, it's usual for people to use your second name. So I was going to be a chemist. That's what I thought I'd like to do. And I was in the chemistry lab, and I remember the headmaster entered the chemistry classroom, and he said, "Ratcliffe, could I have a word with you?" This is where these guys spoke. He was a very frightening man. So I followed him to his study, and he said, "Ratcliffe, I think you should study medicine at university." And I just said, "Well, yes, sir." And we changed the application for chemistry and wrote medicine. So that's how I chose to do medicine. There was no consideration of whether I'd be suitable for it or not. It was just a decision that was made. And then I found my way in medicine, which is different from the way most practitioners evolve their careers. So the answer is I don't know. That was a long answer to the question. It's a good question, but I don't know. And I don't think you should over-analyze your qualities for suitability to this or that. You will find or adapt that suitability.
Thank you. So next question is, now we can, 1 second. Our student now sent it. Елизар, ти можеш? Так, зараз задати питання. Так. Так, зараз звук.
Так, зараз працює. At what minimum level of oxygen we can live?
So at what level of oxygen can we survive? Was that
yes.
the question? Well, it's interesting. Actually, the limit of survival is around the summit of Mount Everest. That's as high as that's the lowest oxygen you can go without needing supplementary. That's about 6%, 6 to 7%, depending on atmospheric pressure, weather, what have you. But it's interesting. The highest place on Earth is about the lowest oxygen that you can survive. Now in the body, the oxygen levels go down much lower, but you're using oxygen gradients in the body to transfer oxygen. And you can't manage in an atmosphere less than about 6, 7%.
And I have also one more question. What is the maximum level of oxygen?
Yeah, well, that's again a good question. You can survive in hyperbaric oxygen for a period of time. That hyperbaric means that the pressure is over that of the atmosphere. So 100% oxygen plus compression will give you like 200% oxygen. Now, that will make you very poorly if your exposure is continued. Quite why is not too clear. It may generate oxygen radical species, which are molecular species of oxygen other than O2, other than molecular oxygen, which are highly reactive and cause cell and tissue damage. So the answer to your question in outline is for low oxygen, you can't survive even short periods of time if you go below 6%. For high oxygen, you can survive, but it'll cause disease over a period of hours or days if the oxygen level is too high. That's probably true of all oxygen. You'll use it in medicine, but you'll always be asked to provide the minimum oxygen to your patients, which provide sufficient oxygen in the blood. So you wouldn't use 60% oxygen if you could get away with 35% oxygen. So I don't know whether you're a medical student, if a doctor would measure the oxygen in the blood and adjust the prescription of oxygen to bring it up to a reasonable level for the patient.
Thank you. Thank you. So next question from the student. What does it depend on the different people start to feel mountain sickness at different altitudes? How then do smokers tolerate it?
Oh, that's an interesting question. I don't know with smokers. Altitude sickness comes in different forms. You're correct, it is due to hypoxia. I have altitude sickness, I have it very badly, so I get pulmonary edema at high altitude. And it's difficult to know what predisposes to that. It's not simply oxygen sensitivity. It's probably something about the way the lung works. So the lung has a system of matching oxygen levels in the breathing bit of the lung to the blood flowing through the circulation. So if your lung is not ventilated, like you've got COVID pneumonia, then ordinarily the blood supply will shut down so that you don't pass unoxygenated blood into the main circulation. Now, it seems that that system is overactive in some individuals at altitudes, probably myself being one, and that leads to excessive shutdown, and then the blood has to go somewhere, so it goes through the rest of the lung, causes lung water to build up, makes a patient very poorly. It's actually this type of altitude sickness is commoner in young people than older people, and probably commoner in men than women. And a possible reason is they're vigorous, they use a lot of muscle power to try to climb the mountain. Of course, that creates the need for oxygen and makes them more susceptible. So it's a curious disease that doesn't correlate completely with oxygen sensitivity.
Thank you very much. So next question is tell us how cells and our body adapts to changes in oxygen, especially when it becomes less.
Yeah, so as I said earlier, what we discovered with beyond EPO, there were many responses, possibly in any cell, 1,000 genes or more respond to the system we discovered. And there may well be other systems that we haven't yet discovered. Those responses affect things specific to the cell, like the cell's metabolism, its complement of mitochondria, the way it uses energy metabolism. Does it do glucose metabolism or fat metabolism? Does it oxidize fat or does it synthesize fat? All of these things are cellular responses to the amount of oxygen that's available. And then there's a different type of response, which is concerned with adjustments of oxygen supply and things like EPO or breathing rate, or as I've said, the way the blood vessels behave. You can blow, the system will, if switched on, will make you grow new blood vessels. That's a hope for some people with, for instance, heart disease. So that the amount of vascularity, the number of blood vessels, is adjusted in accordance with oxygen by this system. And then there are types of response concerned with cell differentiation, cell growth, cell survival that are regulated. As I say, possibly 1,000 or more genes in any particular cell. So many things. And they divide principally into two types, those that affect the cell itself and those like the regulator of blood production or breathing or blood vessels that affect the whole body.
Thank you. So next question is, do you have any tips to procrastinate less and increase learning efficiency?
So again, hook up a little bit. Say again, Yosveta.
Do you have any tips to procrastinate less and increase learning efficiency?
Yeah, that's a good question. I do have an interest in education, and I do have an interest, of course, in science education. This statement's a little bit political, but in terms of education in science, if you want to be a discoverer, then I think understanding the history of discovery is very important. Understanding not just how things are, but how the discovery came about is very interesting. The people who made these discoveries, often very colorful people. It's interesting to know them as people, and it's interesting to know how they made the discovery. That is important because it is discovery that we're teaching, which is not necessarily based just in the facts of the discovery, but in the mode, in the identification of the question and the mode in which the discovery was produced. So I would teach science and suggest that you orientate yourself substantially through the history of science. Now, there's another issue where I would actually teach history through the history of science rather than the history of military conflict or political conflict, because to a first approximation, science drives the development of society. And it's actually been not too easy to persuade politicians of that they don't seem to understand quite how indirect the use of some discoveries is. That you'll be familiar with the PCR test for COVID pneumonia, for COVID infection, that the enzyme that's used in a PCR reaction was found in thermophilic bacteria. These are bacteria that live very high temperatures, like 90 degrees, that would kill you and I. So why would it be useful to study things like that? You have no idea, but it turns out that it is. That's the point. So the world needs to understand that the use of scientific knowledge is often very indirect, so that finding things out is important in its own right. And I'd like to try to teach history in that way.
Yes, thank you very much. So we have a question from a student. So, gotcha.
Okay, so there is a people who live in the mountains from their childhood, and is there any difference in consuming the oxygen or oxygen sensing and the risk of hypoxia between us who live on the flat areas and the people who have been living on the high areas for a long time?
Yeah, good question. Well, there is the short answer to that. In particular, the Tibetan population is one that's much studied. And gives rather clear answers. I think the Tibetan population is the one that's been at altitude, we believe, for the longest, at the highest altitude, and probably went through what's called the population bottleneck. That means that there were relatively few people who migrated to the altitude and formed the population. That means you've got a certain level of genetic homogeneity, a certain frequency of genes in those people. Now, the Tibetans are definitely more able to live at altitude than Caucasian Europeans, and better able than their closest human relation, the Han Chinese. And they probably have polymorphisms in these oxygen sensitive proteins that we discovered that are relevant to their increased ability to adapt to altitude. They certainly have the polymorphisms, and quite how they work, it's not clear, but the Sherpas can climb Everest more easily than the Caucasian people, for sure. And now, different populations on the Andean plateau, it appears to be different. In Ethiopia, on the Ethiopian plateau in East Africa, it appears to be different. So different sub-races of human beings have selected different mechanisms of coping with very low oxygen. It's an interesting, good question, one that a lot of people are studying. Interestingly, Sherpas, the Tibetans, they breathe more at altitude, but they make less red blood. So if you go to altitude, your hemoglobin level will go up and your breathing level will go up, but perhaps not so much as would happen if you're a Tibetan. They breathe even more strongly, and perhaps because of that, they don't get as so hypoxic in the body, and they don't produce quite so much EPO, and they don't get this very thick blood, which causes trouble in many people who try to live at altitude.
Thank you very much. So next question is, 1 second. Could oxygen be replaced with another element in the physiological processes?
Well, it has distinct chemistry. So I think broadly, no, not in terms of human life. I mean, just to speculate a little bit, people ask sometimes, is there other life out there? How would it be? And my view is, I think there must be. I can't imagine that it would be otherwise. And I believe that life as we know it on Earth did come from elsewhere. It's a statement of belief, not fact. I don't know it. But you have to ask the question, how would life be if it evolved in another place, if there's more than one evolution? And the answer is it may be much, much, much more different from the way you think it is. My definition of life, there are many, formation of cells, replication, is really that it's homeostatic chemistry. So you understand the difference, the homeostatic and ordinary chemistry. The first piece of reductionist biology, I would say, was Antoine Lavoisier, the French chemist. And he discovered the chemical equivalence of burning charcoal and the metabolism of a guinea pig. So he said that it was stoichiometrically chemically equivalent, and that explained a piece of biology by chemistry. But the huge distinction is between combustion and metabolism is your metabolism is regulated. You don't burst into flames and go up like a fire. So somehow, whatever chemistry is used, whether it's oxygen or some other element, it has to be adapted in a homeostatic way. But I'm not a chemist now, but I believe that other elements would be capable of supporting homeostatic chemistry. But you would look quite different, unrecognizably different. It wouldn't be human beings with green teeth or something like that. They would not be recognizable as human beings, and probably not recognizable as cells or chromosomes or any other building blocks. But they would have to be homeostatic, in my view, to reach the definition of life. Interesting question.
Thank you. So the next question is, how did you feel when you get the Nobel Award? How did you feel?
Well, it was an interesting morning. That's true. It always happens on a particular day, the first Monday in October. And actually, I'd forgotten that it was the Nobel. What happens is people keep hinting beforehand. People keep hinting to you, or you can even place bets like a horse race on whether you will get the Nobel Prize. You can go to a betting agency and you get 8-1 on me and 10-1 on someone else. So that is a slightly uncomfortable position. But I hadn't anticipated the call. My secretary, who's just outside, took it and said very excitedly, came up to me, said there's a call from Stockholm. So we knew what it might be about then. Of course, you've got to be careful because people play tricks on you. So you've got to make sure it's not one of your friends playing a trick on you. And the person making the announcement, Thomas Perlman, he takes his time. This is Thomas Perlman. I'm calling you from Stockholm, which is in Sweden. Of course, we all know that. where the Nobel Prize is awarded by the Nobel Assembly, of which I am the secretary. And he takes his time to get to the bit that you have won the Nobel Prize. And then things happen very quickly. There's a press announcement, and I think people were very kind. I had 3,000 thank you letters to write. I had 3,000 messages, so that's quite overwhelming. For a time, even my children thought I had something to say about issues in life. That doesn't last very long. They change their mind, and their father has nothing useful to say quite shortly afterwards again. But almost overnight, at least some people think you've been endowed with infinite wisdom. Of course, nothing has changed and nothing much will change, but it's an extraordinary experience. Actually, going to Nobel Week is an interesting experience, like being a celebrity for a week, which is probably about as long as you would want to be a celebrity for. You just have it for a week. It's like a vision of a different life. The Swedish royal family, the whole thing is sort of extraordinarily well organized, and you have a great time in fairyland, and then you come back to real life, which isn't that much different.
Thank you. So next question, can some organism potentially be suitable to breathe heavier isotopes of oxygen?
So some organism potentially be suitable for what?
Breathe heavier isotopes of oxygen.
So again?
Breathe heavier isotopes of oxygen.
So I asked Catherine, just come and try and hear this question. There's not completely good. Just.
Okay. Can some organism potentially be suitable to breathe heavier isotopes of oxygen?
To what?
So are they isotopes?
Suitable for what? We've got the organism.
To breathe.
To breathe.
To breathe.
Can some organism be, other organisms be suitable to breathe oxygen?
Yeah. Can some organism potentially be suitable to breathe heavier isotopes of oxygen?
Heavier isotopes of oxygen, did you say?
Isotopes.
Yeah. Isotopes.
Sorry.
Yeah, no, that's okay. Well, an isotope would be similar chemically. That's the definition of an isotope. So we can all breathe heavy isotopes, and indeed we do that to investigate where the oxygen goes. I mean, oxygen 16, but you can buy oxygen 18. You can breathe oxygen 18, no problem. It won't do you any harm. It's going to cost you an absolute fortune to do so. It's probably to breathe oxygen 18 would be what? £1 million a minute. But it wouldn't do you any harm. It's chemically the same. So the isotope will not alter the chemistry. If it's a radioactive isotope, of course, then it'll cause radiation damage to you. But that's a different question from the chemistry.
Okay, thank you. So next question. Are there special adaptive mechanisms of cells with an increase in the concentration of an inert gas in the environment?
That's an interesting question, to which I don't know the answer. Your question is, could some inert gas be concentrated and used physically to protect the cell? Not to my knowledge. Of course, people have tried to produce they're not inert gases. They're molecules which which affect freezing behavior and are concentrated in cells to enable animals to be frozen without killing them. They're antifreeze, so there are sort of that's a little bit, it's not the question you asked, but it's a little bit analogous that there is chemistry that's used to protect special cells against very unusual environments. But they're different from oxygen.
Thank you very much. So that's all. We haven't the question. We all thank you to your support. It's very important to us, especially at this difficult time in Ukraine. Thank you.
No, I understand, and I wish you all well in every possible way.
Thank you very much. I hope we see you again.
Indeed. Yeah. Okay.
Thank you. So we finish this session. Goodbye.
Bye-bye.